our host is recording, right? Or is going to Junle? I guess it's Junle. He is recording. He's responsible for the recording. The host. If not, maybe some other. Oh, okay, okay. So, so we can, I think we can start our
a few minutes.
Still 2 minutes? 1 minute.
3 minutes.
Okay. Oh, Manuel.
Hi.
Hi. Oh, for a long time I haven't seen you. Oh, am I changed?
Somewhat.
Oh.
For the better, of course.
Mm-hmm. Mm-hmm. Oh, how are you?
I'm okay. People are still coming in, it seems.
Okay, now let's start our second plenary session today. And the first speaker is Professor Ignatios Antoniadis, and he will talk about challenges in supersymmetric cosmology. Please.
Thank you very much. Share the screen.
Yeah. Okay.
Okay. So I would like to thank the organizers for putting this enormous meeting online. It was a big challenge. I would prefer, of course, to be there. Okay. So I would like to start briefly with the motivation, starting from the various scales that appear in any fundamental theory that would like to describe at the same time particle physics and cosmology. So one hand, we have the like to extend the standard model. We don't know if there is any physics such as supersymmetry within the LHC energies or nearby energies. But supersymmetry is a well-motivated proposal addressing several open problems of the standard model that I have here, you can read. It is a supersymmetry conference. But on the other hand, we know that there is no experimental indication, but not only supersymmetry of any beyond the standard model physics, apart from some small deviations. However, it is likely to be there at some more fundamental level. A second scale is the scale that one can find from the dark energy, which is in the simplest case is a small cosmological constant, which satisfies the same equation of state as the one which fits lambda CDM of dark energy when we put the cosmological constant on the other side. Then from this point of view, there are two scales. One is classical scale that's associated with the cosmological constant. And this scale can be inferred by the Hubble parameter. And it's essentially the size of the observable universe. While the other scale is directly related to the dark energy, which can be translated into length to the -4. But for this one, you has to use the h bar, so quantum Planck constant. And this scale is much different from this one, and it corresponds to energies about a milli-electron volt, which I put here. Another scale that would be relevant for my talk is the inflation scale that describes a possible accelerated phase of our universe, which is approximate de Sitter, but with a value corresponding to a value cosmological constant, which is much different than this one. The inflation is a theoretical paradigm consistent with cosmological observations, but it is based on phenomenological models with no real underlying theory. It is parameterized by a scalar field that it is introduced that drives universe expansion at early times, with a potential which has some region quite flat, in which standard paradigm is to have a slow roll, which means that in that region, the first and the second derivatives of the potential are small compared to the de Sitter curvature. So these are, of course, these are three scales that are besides the Planck scale. And my question is what is the physics behind them, and if there are connections. So what I will discuss in my talk is a proposal that was put forward some years ago, which realizes a direct connection of two of the scales of inflation and supersymmetry breaking. Both of them are unknown. We don't know the scale of inflation. We don't know what is behind it. And similarly, we don't know what's the supersymmetry breaking scale and if it is realized naturally. So this direct connection will be realized by identifying the inflaton with a partner of the Goldstino, which is a Goston fermion of spontaneous supersymmetry breaking. While at the same time, we'll try to accommodate the observed vacuum energy, but without trying to explain it. So because of relation of supersymmetry and inflation, we had to start with a reminder of the main problems in supergravity by making models of inflation. So the inflaton should be first part of a chiral superfield, so it's complexified. And immediately in supergravity, the first problem that one encounters is to satisfy the slow roll conditions, and more precisely the eta problem, which requires some fine-tuning of the potential. So that's the known expression for the scalar potential. I mean, here I take derivatives as I ignore the fact that the field is complex for simplicity. K is the Keller potential, W is superpotential, and D is the Keller covariant derivative in Planck units. So the point is that if you take the inflaton to be a canonically normalized field around the inflation point, which I can choose to be the origin, then the second derivative if I take the second derivative here of the Keller potential, it goes to 1, and then it gives back the potential. So eta comes with a contribution 1 from this term, plus, of course, other contributions which are model dependent. So this is the fine-tuning consists of canceling this one and replace it by something small. One possibility to go around this is by considering non-canonical kinetic terms, such as, for instance, the framework of no-scale models, which have zero potential and constant superpotential. Typically, however, the models that one generates in this way is that requires a large field inflation and require transplanar initial conditions that break the validity of the effective field theory. And of course, in that case, there's no way to justify why you take this particular form. And actually, the Starobinsky model is part of it. It has also this problem, theoretical problem. Another issue is that because the inflaton is complex, there is a phase, an imaginary part, pseudoscalar companion, and this must be stabilized so that it does not create a problem during inflation. And then there is a series of other problems which are more framework dependent, such as moduli stabilization, string theory, the questions about the Sitter vacuum and so on. Now, let me then describe you from the beginning how this idea to identify the inflaton with a Goldstino superpartner can cure this problem. So the first observation is that if the Goldstino, if the inflaton belongs to a Goldstino superfield, then the superpotential has a linear term. And then for a linear superpotential, there is an exact cancellation between the one that you find from the expansion of the Keller potential and a contribution that you get, negative contribution that you get from the Keller covariant derivative. So for canonical kinetic terms, eta starts with 0. Then there is a question, can we then be based on this observation and guarantee that the superpotential is exactly linear? This can be done by symmetry, and this symmetry is an R symmetry because the superpotential is charged under the R symmetry. If the R symmetry was global, then the breaking of the R symmetry away from the origin would imply a Goldstone boson. And to get rid of this, the proposal is to gauge the R symmetry. Then the pseudoscalar companion of the inflaton, the phase, if you want, is absorbed by the R gauge field and becomes massive. And one is left over only with one scalar field, which is the inflaton. Then I will assume that inflation is of the type of the hilltop. In other words, that the origin corresponds to a maximum of the Keller potential, and then one will get a small field with inflation with no large field initial conditions. And finally, the last point is that we'll use the fact that there is a gauge symmetry to balance the vacuum energy at the minimum between the F term contribution and the D term contribution. So the picture will look like this, where rho is the absolute value of X of the inflaton. So as I said, when the canonical kinetic, for canonical kinetic terms, eta is exactly 0. So we'll to obtain a non-vanished in eta, need to obtain a maximum with a small curvature. We'll add a correction to the Keller potential, which is quartic, and which should have a coefficient to be positive, so that the origin corresponds to a maximum. In this way, the smallness of the eta will be directly associated to the small correction of the Keller potential. Will be suppressed, let's say, by Planck scale or some other scale of the underlying theory. Then the superpotential is linear by symmetry, and assume the kinetic term to be 1. There is a question of anomalies here, but it doesn't play any role. I don't have time to explain. So the full scalar potential is a sum from the F terms and for the D terms, which are controlled by different quantities. One is the F coefficient here, the Goldstino decay constant, and the other is the charge, the U1R charge of the Goldstino. And we'll assume that the inflaton happens around the maximum, so around here. Then one can compute the slow parameters in perturbation theory around maximum. The eta, as I said, is directly related to the correction, the first correction here, capital A, which is negative, so because A is positive. And the other slow parameter is proportional to eta square times the the value of the inflaton around the origin, which are both less than 1. So epsilon is guaranteed to be much less than eta. Inflation should start with some initial, with an initial condition at the value which is near the maximum, which corresponds to the exit of the horizon, and will end when eta goes to 1 as the field goes down. Goes down the potential. The number of efforts can be calculated in this approximation, and is given by this formula: 1/eta times logarithm of the displacement of the field at the end of inflation divided by the value of the field at the exit of the horizon. And here, since epsilon is much less than eta, then from the Planck data, from the spectral flow, one needs an eta which is around minus 0.02, which automatically gives you here a number 50. And therefore, one obtains the automatic number of efforts that we want. So putting together all the predictions, the relevant quantities for inflation, which is the amplitude of density fluctuations, the spectral index, which is given by the eta, and the tensor to scalar ratio, which is given by epsilon star. Using the observed values for the spectral index and the amplitude, one finds that the scale of inflation should be less than approximately 10 to the 12 GeV, and the ratio R of primordial graviton waves should be less than 10 to the minus 4. So this is the proposal, which is I find very natural to get the right numbers by just starting by this postulate. The question one can ask is about the next question one can ask is about the minimum. Whether that minimum, of course, if it is far from the origin, then one cannot make perturbation theory around. So the question is, can a nearby minimum exist with a tiny vacuum energy? The answer is yes. And for this one needs, at the same time to take into account the D-term contribution, which I ignored here. I assume that the charge is small compared to the F term. And then one needs also a cubic correction to the Keller potential, which is to add an extra correction here, which is xx bar cube. It would be interesting to find a microscopic model which gives this effective field theory, and this is what the first step of such microscopic model at the level of supergravity is going to present it here. It's a model based on a Fayet-Iliopoulos term, it's a Fayet-Iliopoulos model, but you have to replace the U1 symmetry, the standard U1 symmetry, with a U1R symmetry. This U1R is not the same, which it's responsible for the inflaton that I described before, but it is the one which is will give rise to the effective field theory of inflation that I wrote before. So the main observation is that I mean, as usual, the Fayet-Iliopoulos model uses two chiral multiplets with opposite charges. However, here, since the U1 the edge is the R symmetry and the superpotential has a charge, the charges of the phi plus and phi minus are not opposite, are not equal and opposite. They have to be different, the sum have to be different than zero. So this is also the reason why this model has to be done in supergravity. You cannot make it in global supersymmetry. Then one goes to the Higgs phase, to the region of the parameter space, which corresponds to the Higgs phase. I can, for instance, assume that phi minus gets a vacuum expectation value, which of course is related to the parameters, to the underlying parameters of the model. And one can look at the limit of small supersymmetry breaking compared to the U1 mass. What happens is that the phi minus, let's say, will acquire, will give a mass to the U1, which will become heavy, and the Goldstino will be inside phi plus, which remains massless. And in this approximation, one can integrate out phi minus, sorry, and leave an effective theory with phi plus, which has a constant superpotential and a Kähler potential, which can be expanded perturbatively in powers of phi plus square. And then one can compute the coefficients of A and B, relate them to the underlying, the parameters of the underlying Fayet-Yopoulos model. And one can check that the parameter space of the theory allows indeed to do a realistic inflation and at the same time have a nearby minimum, perturbative minimum with a tunable energy, for instance, 0. So that's an explicit example, which would be a first step towards finding a more fundamental theory beyond supergravity, such as, for instance, string theory. The next question is whether here I described the whole scenario of inflation was based on F terms, on the F term, or the linear term. The D term was there for two, the U1, the gauging of the U1 was there for two reasons. One was to absorb the pseudoscalar partner of the inflaton, and the second is to allow for the tuning of the vacuum energy. You can ask the question, is it possible to get to have inflation with the same properties, but using a D term, not an F term? The problem is that the Fayet-Yopoulos term supergravity is very restrictive. In general, it gives a large positive mass to the inflaton. This Fayet-Yopoulos term exists only for a gauge symmetry, which is our case. This is just to tell you that's a D term. So you see that in terms of there is a charge factor and there is a quadratic term, which is with coefficient 1. So it is impossible to make to satisfy the slow-roll conditions with this term. However, recently, relatively recently, 2-3 years ago, a new Fayet-Yopoulos term was written, which is gauge invariant at the Lagrangian level, but it is singular as one sends the supersymmetry breaking scale to 0. In global supersymmetry, it can be written explicitly in the superfield like this, where W is the gauge kinetic term superfield of the U1. This can be expanded in components. So the bosonic piece is exactly a term which is Fayet-Yopoulos term with some coefficient psi1 here. And the rest of the expansion contains just powers of fermions. And they have denominator, which is D, which is singular as D goes to 0. So one has to assume that D is non-zero in order to write this Fi term. There is also an interesting observation that if you couple this theory to supergravity, just this U1 with a new D term, then this fermion is the gaugino, which is the Goldstino, because this is the only, supersymmetry is broken by the D term.
3 minutes.
Sorry?
3 minutes.
Therefore, I can go to unitarity gates, in which the gaugino is 0, and then one obtains the standard supergravity with a cosmological constant. This D term can be generalized in the presence of matter. It gives a potential of this form, K is the Kähler potential. And then one can show that this nu and the standard Fi term can coexist in a particular Kähler basis. So in which the superpotential is constant by Kähler transformation, and then one has an extra term in the Kähler potential. Then the D term is modified in this way. So now one can, to understand what happens, one can set the F term equals 0. Then one has just a D term. And the condition that this potential has a maximum at the origin fixes b, which is the coefficient of the log, to be 3, and this coefficient psi must be less than -1. At the end, one gets a potential where one sees that 1 plus psi parameter plays the role of the correction a to the Keller potential in the F-term inflation that I mentioned before. Because for this particular value, the coefficient of the rho square term eta vanishes. But of course, in that case, it's put by hand. The effective charge vanishes, but there's no other symmetry. Of course, the minimum now is supersymmetric, but since the new Fi term is singular at the minimum because of the fermions, one needs a small now F term, and this small F term uplifts a bit the vacuum. The supersymmetry is broken by both D and F terms. And these are the predictions, I mean, the formulas for the various parameters, which are similar, exactly the same actually with the previous model. The difference is that A is replaced essentially by 1 plus psi. The advantage of this model is that if now one examines also here, this analysis was for canonical kinetic terms. If one announces now corrections to the Keller potential as before, then one can increase the value, the prediction for R, for the ratio of gravity waves, and can be done as large as 0.015, which is near the experimental bound. So I think my time is over. Just to say that this new Fi term it introduces this potential which breaks scalar invariance. One can ask how one can modify this term to respect scalar invariance. The answer is yes, it can be done. In the simplest case is again a constant uplift potential, which is in the presence of matter, which is an interesting possibility which was recently discussed in the literature and can be even generalized in equal to supergravity. So I would like to conclude just saying that I present a general class of models with inflation from supersymmetry breaking by identifying the inflaton with a Goulstino superpartner. The R symmetry is restored at the inflation. It's a small field, it avoids the eta problem, and it has no scalar companion, while in principle one can find a nearby minimum which has a tunable cosmological constant. It can be also done with a D term, as I mentioned before, using this new Fi term. The open question is whether this can be realized in string theory. I said the first case I present you a microscopic model within supergravity. Now, in string theory, the challenge is to find if it is possible to gauge the R symmetry, or in the case of new Fi terms, if they can have a string theory origin, and then, of course, to make explicit model building. So, thank you very much.
Okay, thank you. Thank you for the interesting talk. Now, is there any question? Yes, please, Takahiro, please.
Yeah. So do you have some comments about the low energy supersymmetry breaking scale after inflation in your framework?
No, in principle, I mean, during inflation, supersymmetry is broken. At the minimum, in general, I expect the supersymmetry to be broken. But the scale at the minimum is not. One could try to get to make this model as a toy, as a hidden sector of to transmit the supersymmetry break in the standard model. But I'm not sure how low the supersymmetry scale can be done without requiring to have inflation also. It can go low at the TV scale, but requiring also to produce inflation, which fixes the normalizes the potential, it's not clear whether it can be done. So in principle, I would say the supersymmetry breaking scale will be high, but how high, I don't know. It's an interesting question to study.
Okay. Apostolos, please.
Okay, very good. Thanks for this very good talk. I try to understand how much of all that what you said about F-term and D-term inflation will be discussed before in the context, also, as you know, in the hybrid inflationary models, and similar conclusions derived. Of course, in that case, back in, using different similar terms, which you also included by Copeland et al., and also went beyond the three-level approximation, which it seems that you only consider you did not consider radiative corrections. So I try to understand how much of that, including radiative corrections and all that stuff, are different in your framework. What is the difference here?
I understand. The linear term in the superpotential, it was known before. But the precise suggestion to make it to gauge the arithmetry in order to be exactly linear and to have this setup which the inflaton is exactly identified with the partner of the Golstino was not known before. Concerning radiative corrections, of course, that was in effective field theory. The closest that I could be was within this microscopic model of supergravity, because there is an explicit, it's a Pagliolo, it's a Pagliolo-Liopoullos term coupled to supergravity, but since this U1 is an RU1, it is not really a normalizable theory. It's supergravity, but it's not a normalizable theory. But still, you can make the integration out and find the effective theory, that the structure of the effective theory that I used before for inflation. So that would be a first step towards.
And of course, there are other variants which also worked on in the past, which are F term with a D term, F sub D term, and so on, of hybrid inflation, which give similar predictions or may have similar structure, not exactly the same you are discussing.
I mean, the main information.
It would be interesting to see how unique or how
symmetry
different are the structures.
That's a symmetry principle behind, which, by the way, fixes also the initial conditions. Because it's symmetric.
Yeah, the hybrid models have also that starts Planckian. They have this beautiful feature. They don't have this problem as Transplanckian effects. That's the reason why.
No, but this is not Transplanckian. It's small scale, small field deflation.
Yeah.
This model was small.
Small field. Okay, I see.
Okay, thank you very much, Professor Antoniadis. Because of the time is limited, we need to shift to the next talk. The speaker is Professor Rohini Godbo. She will talk about aspects of Higgs and the electroweak physics in supersymmetry, light, ARSP, and Higgs, heavy Higgs.
Okay, thank you very much. Can you confirm that you can hear me?
Yes.
Okay, thank you. And now we are going to change, I think, the tracks completely from this very formal talk to a much more phenomenological talk. And what I'm going to discuss here is, as is announced, aspects of Higgs and electroweak physics. This was the title or subject given to me by the organizers. And I decided to choose these two because now, in the absence of any evidence so far for supersymmetry, we really need to think of the nooks and the corners where we need to look for it from different motivations. And I have chosen two corners, which I think are perhaps the very promising ones, so or at least to get some kind of definitive answer. So first I will, and I also, if time is left, I would like to point out to all of us phenomenologists, experimentalists who do these studies to once again tell the importance of the precision calculations for the Higgs sector that now plays in these studies. But before I talk about anything, I wanted...
Excuse me. Would you share the screen, your screen?
Oh my God, I never did. Thank you. Thank you very much. I just forgot. Where do I share it? 1 second. Where is the share screen? Ah, here it is. And yeah.
Okay.
Can you see my screen now?
Yes.
Is it full view? I'm really sorry. Okay.
Yeah, it's in flow.
Okay. But anyway, not much is lost since I didn't start anything so far. Thank you. So as I said, I wanted to really begin this talk by paying a tribute to Steven Weinberg. As is in every other aspect of particle physics, he left a defining legacy in supersymmetry. And I thought I would remind ourselves, since there are perhaps young people in the audience, that he was one among the three who defined naturalness, which was the issue of scalar masses in the context of grand unified theories, which sort of pervades our supersymmetry discussions through the years. Then supergravity effects as a messenger of supersymmetry breaking. He contributed very importantly to that. And for a personal reason, I have put a third one, which is perhaps not so well known. And this is a paper he wrote on showing, I will show it here, a paper he wrote in 1983, where he said that in a large class of broken supersymmetric theories, they imply existence of fermions, the gauge fermions, which are lighter than or nearly degenerate with the W plus and the Z bosons. And at least for me particularly, this was the time 1983, and W's and the Z's were just being studied at the Tevatron, and little after that, and one kind of thought, oh, can we look for neutralinos and charginos in the decays of the W's and the Z's? So therefore, for me, this is a very interesting paper that he had. Now, right now, what is the situation from LHC? We have very strong experimental constraints on the masses of all the various kind of particles, and they are essentially in simplified models, and many are constrained to have rather high values, and those that are still allowed to be lighter are in the electroweak sector, and then they can be translated into constraints on the SUSY parameters of the theory. I'm not going to discuss this at all, but just to show you, I have taken this from PDG, and this is, the limits have become only stronger. But what I liked a few years back was Atlas had produced that how these limits translate in PMSSM, because those are simplified model limits, onto the masses of the particles. And this is the statement that I was making, that the limits are weakest for our neutralino or for the Stauwan, etc. So in the as a supersymmetric standard model, there are a supersymmetric dark matter, there are two candidates. One is this neutrino and in the PMSSM, and the other is neutralino. Whereas this neutrino actually has full strength gauge couplings to all the standard model matter, and as a result of that, a light neutrino left-handed can never be a good dark matter candidate. It was also ruled out by direct detection experiments long back, and therefore we are focusing only on the neutralino as a SUSY dark matter. So I will base most of my discussion on this review we recently wrote, and the question that one wants to ask is how large can a SUSY LSP candidate be and still be a viable dark matter candidate. And what is meant by this? What is meant by this, that it should not overclose the universe, and it should satisfy, of course, the direct and indirect detection constraints. Then it is a viable dark matter candidate. Now, how do we know how to decide whether it overcloses or undercloses? So for that, we know from the Planck measurements of the anisotropies very accurately that omega is 0.120 plus minus 0.001. And in a model calculation, the thermal, assuming thermal relic, that is the temperature, the relic density, which is decided by the temperature at which the particular species falls out of thermal equilibrium, or what we call freeze out, then the expression is given here. And this expression basically says that larger is the cross section, smaller will be the relic, and smaller is the cross section, larger will be the relic, depending on this typical annihilation cross section, which is velocity weighted. Now, in the usual scenario, when we have derived this, one assumes that the expansion of the universe is adiabatic, and if there is an entropy injection or something like that, it could dilute this relic density. So therefore, I just want to say that one could think of different possibilities which then give the right relic density, and therefore, in principle, I will divide my discussion into two parts. One where the SUSY parameter does not overclose the universe, and the other where the relic is perhaps higher, and one might have to depend on non-standard cosmology. So before I begin by saying how light it can be, first let's just ask whether theoretically, cosmologically, do we have any limits on cold dark matter, mass of the cold dark matter particle? And there are these very nice papers by Céline Bohm and collaborators, which actually tell us that masses for CDM as small as 2.5 MeV neutralino could be really allowed. Now, what about details from the detection of dark matter? There are some reported low mass LSP direct detections, but looks like that they are perhaps due to experimental fluctuation, or they are not dark matter, at least not conclusively so. In case of indirect detection, the lack of clarity due to uncertainties with astrophysics really tell us that we cannot right now pay too much value to those detection results. And the current limits, status of the best limits, which are from xenon 1 ton, is shown here, which were published in 2019. Now, the question that we want to ask is that how low can a mass of a viable dark matter candidate be in supersymmetry, which is consistent with all these different exclusions that one is talking about. And then, of course, one wants to ask the next question, can the future colliders probe these light LSPs? So, other way of saying it is, can we rule out this region using collider experiments, using phenomenology of the heavier electroweak units? And the other question that one can say is that if tomorrow a light dark matter particle is reported in either direct or indirect detection experiments, can our models and the observed relic density support such a light SUSY dark matter? So, we want to ask these two questions. Now, remember that the predictions for relic density, direct, indirect detection, and LHC phenomenology in the case of supersymmetry is all decided by the same parameters, that is the couplings of the neutralinos and the charginos with the standard model particles are essentially decided, or the various particles are decided by the same supersymmetry parameters. So, in case of SUSY dark matter, we can actually look at implications for all the four things. Now, in PMSSM, this neutralino, lightest neutralino, is a mixture of Higgsinos and gauginos. And for NMSSM, there is an additional singlino also. And the additional scalars in NMSSM and pseudoscalars are also doublet singlet mixtures. And the extent of these different mixings decides the couplings of the chi1 knot, and also, for example, the charginos, etc., with matter as well as with respect to all the different Higgs bosons. What I will do here is that I will discuss perhaps two cases in detail. One is the PMSSM, where, as I already showed you, that the weakest LHC constraints from non-observation were on the mass of the neutralino. And the important parameters here are the mu m1, m2 and tangent beta, and radiative corrections will then bring in dependence on AT and MT. I will discuss this both in the context of standard and non-standard cosmology, and in case I don't get to it, the final line is that LHC, a combination of LHC, invisible width of the decay width of the Higgs, and the neutralino chargino searches at the LHC will actually, and the direct detection experiments will actually be able to close the entire, cover the entire region of the light neutralino in the case of PMSSM. In case of NMSSM, the same happens to be true, where you have, as I said, additional light pseudoscalars, and the parameters along with mu m1, m2 and tangent beta and AT, MT are also kappa, lambda, A kappa and A lambda. Now, there are few rules of thumbs and which are known to all of us who worry about supersymmetric dark matter, that a Vino-like or a Higgsino-like neutralino will have to be lightest neutralino, chi1 not twiddle, will have to be heavy to explain the observed relic. Now, how a model can produce a Vino-like SP will be a different question altogether, and I wouldn't even go into that. But a Vino-like LSP would have meant too high a relic density because of the smaller cross sections, and therefore you had to have additional co-annihilation annihilation possibilities, which will then increase the annihilation cross section and stop the universe from overclosing. In general, a T-channel light lepton, this was in the early days, or a resonant annihilation by the Higgs or the A or the Z, these all would actually would allow the additional annihilation channels for a Bino-like chi1 not twiddle, and for the various exchanges you would need a non-trivial Higgsino fraction also in the neutralino, not just Bino, and this is the so-called well-tempered neutralino. So early on, when direct detection experiments were not in full force, the collider bounds were actually dominating the story, and at the lab time in constrained minimal supersymmetric model, or MSUGRA as what we call it, the lab constraints on the charge-ino masses and the universal gauge-ino masses hypothesis of CMSSM already would have ruled out a light chi1 not twiddle. So a light chi1 not twiddle necessarily meant non-universal gauge-ino couplings, and the focus moved to PMSSM or some other versions of MSSM with non-universal gauge-ino masses. So before xenon 1 ton and as well as the LHC results, the older relic density measurements also, there was a lower limit of 30 GeV on the mass of the neutralino, and this was in these papers in about 2011. Now we have much more precise determination of the relic. I told you already how precise it is. There are very strong constraints from the direct detection. I also showed you the plot from 2019. We also have a lot of exclusions from LEP that I didn't show you, and a lot of exclusions from LHC. Apart from that, we have a very important thing which was not available in 2011. We have the Higgs, and we know its mass, we know its couplings, and we also have precision calculation of the Higgs mass. So what is the situation in view of all these inputs? So before I move on, I wanted to sort of give you a summary from this review that was written by Leszek Roszkowski and his collaborators, and we forget about the rest of the plot. It's very, very busy, but what I want to show you is that in his version of whatever MSSM version he was looking at, the MSSM of the neutralino of about mass 30 GeV was still allowed, and note that this is in 2017 where the xenon 1 ton experiment had still not come. So the Higgsino-Bino mixture is something that is liked by the relic, which I explained. So this gives sort of a right relic, but it also means that if the neutralino is a mixture of the Higgsino-Bino, then the Higgs actually can have appreciable branching fraction into the invisible neutralino pair. And in fact, this was the focus of our early papers, which we had started writing in 2000 and continued till about 2013. So the Higgsino-Bino mixed state was liked by relic requirements, and they also would cause Higgs to decay invisibly. Luckily for us, the invisible decay of the Higgs can also be searched at the LHC. So what are the current base limits? The current base limits are about 13%. This is from the Atlas report. The future for looking for this dark Higgs is quite bright. LHC and also the ILC or CLIC or FCC can measure it to very small numbers. So what did we first do? At least what I want to show you first is a light chi1 not twiddle dark matter at the collider in PMSSM. I already explained all this, that a pure Bino will overclose the universe, but a mixed Bino Higgsino give you an efficient annihilation via the Z or the H125, and therefore you will have a funnel region. We chose this region of parameter space just to make sure that we are going to get this, and we restricted ourselves to m chi1 not less than mh by 2. And then what we do is that we make sure that a given point is allowed by a variety of current constraints, LHC constraints, LEP constraints, flavor constraints, Higgs sector constraints. Then we also calculate the invisible branching ratio for the Higgs. We calculate the expected direct detection, spin independent direct detection cross section. The spin dependent one almost never constrains anything, and calculate the relic density for the given point, and calculate the ratio of calculated release density to the observed one. If psi is less than or equal to 1, then it's thermal DM, And if xi is greater than 1, then only time this might be allowed if the cosmology is non-standard. So this is earlier. Let us talk about the thermal density, and this is my result in 2017, where we did not have the xenon 1-ton results. And mind you, this is the branching ratio of the Higgs into invisible. And these it says the whole ash color points denote all the points that we actually scanned with all the constraints put on them, and the final constraint from the invisible Higgs decay from the LHC result, which was coming from the Higgs rates, actually allowed only these points in the Z funnel region and the Higgs funnel region. Now just see what happens when the 2019 measurement of xenon 1-ton came. Almost all the points from our Z funnel region actually disappeared. Only a very small region was left, and the Higgs funnel region, quite a few points were left. Then we asked ourselves whether this small region of blue points, what happens if we allow the current LHC electroweak searches, that is production of charge-neutralinos. And this we did by simulating the production of electroweak pairs decaying through mediation of WZ or WH, leading to these final states. And I won't bother you about the detailed results, but the funny part was that once we did that, I don't think you can see it, there are only 2 or 3 orange points which are left. So it looks like that perhaps now the current LHC results with xenon 1-ton more or less excludes the Z funnel region completely, and we are investigating this a bit further. But then we decided to ask the question, how can these points be, whether these points can be investigated at the HLLHC. This is just a description how we implemented the LHC run to constraints to make sure that these only 3 points here are allowed, and these are all the points that are allowed. I will skip that. And then what we saw is that again using the same production of electroweak pairs at the LHC, high luminosity LHC, we saw that these points that were here, these orange points, we saw actually that one could in fact probe some of them at the HLLHC. At HLHC you could probe all of them, and this is sort of a very nice thing that MSSM low mass neutralino window can be probed through this associated charge-neutralino phenomenology when the neutralino is a thermal dark matter. In case this neutralino is a non-thermal dark matter, that means xi is greater than 1. So here you see that this blue actually indicates points that are even below the neutrino floor, so direct detection will be inaccessible. I am not showing you invisible decays, but this region is also not accessible in invisible decay. But the production of charge-neutralinos will be able to cover this region. So that also looks to us quite exciting. Now, in the case of NMSSM, the superpotential gets an additional term, 2 additional terms depending on 2 parameters, lambda and kappa. And now the neutralino mass matrix becomes 5-dimensional. You have the singlino, the LSP is a superposition of all the 5. Now you have in the game one more pseudoscalar and scalar in addition to the MSSM Higgses, and they can become available for resonant annihilation, and these additional annihilation channels actually make now a light neutralino possible. This is a much studied subject, particularly recently, and our focus was looking in detail as to how the mass region less than 65 GeV, what part is still allowed in light of all the current constraints, and see the connection with invisible width. Before that, let me just show you that there are these 2 groups which have been working very consistently in this NMSM area, but this one is in a semi-constrained NMSSM, this one is in general NMSSM. Again, we chose our regions of parameter space such that which will give us a neutralino which is light enough, and again when we do all the game, we play our games now because of the annihilation through the A1 and H1, which is the light pseudoscalar and the light scalar. This annihilation channel allows us that the neutralino will not overclose the universe. Now we are only looking at the thermal case, and what you can see here is that there are xenon 1-ton still cuts its way through, but there is really a large amount of region where the neutralino is lighter than 65 GeV, and in NMSSM the whole region is allowed, and there is a lot of region here which is below the neutrino flare again. Sorry?
3 minutes left.
Okay, thank you. And the question that we asked is, can you probe this in HLLHC and HELHC? And again, we were able to do a decent simulation, and this simulation showed us, and these are the results which were recently published, that indeed this entire region that we have got can indeed be probed through the 3L plus ET slash and 3L plus ET slash WH mediated or WZ mediated chargino-neutralino production. I will skip this in view of the time because I do want to tell you about something which is not my own work, but which really came home to me very strongly in a talk that was listening to a talk given by Margaret Mühlleitner. So I wanted to share it with you, that when we do all these current experimental constraints, we use various tools, experimentalists as well as phenomenologists, when we do our parameter scans. And then we say most of the important ones right now are the ones that are coming from the measurements of the Higgs mass and the coupling. And the situation is now such that the precision of the calculation matters. So the question in MSSM, we really have a very detailed job that has been done over many years. It's almost complete. Maybe the case where particle spectrum is very heavy is still sort of, there are some few hitches, and there is a very nice review. In the case, and I will again skip this. This is a summary which I had picked up from this talk by Margaret Mühlleitner. And there is a large number of groups that have been working for many years. And I'm going to take the example of the NMSSM calculations, which include, and the recent ones include CP violations, SUSY QCD corrections, as well as SUSY electroweak corrections. And there is this variety of papers which I have put here. But what I want to show you, and that is really the point I want to share with you. And this is a plot I have taken from this latest paper from this group by Mühlleitner. And what you see here, this is, you have to look at this here. This is the Higgs mass in two different correction levels. The red is the one when the full electroweak corrections, including those corresponding to lambda and kappa in NMSSM, are included. And these are the ones, the black line and the blue line is when you have only included corrections which do not come from lambda and kappa, and you really see in the insert really a big difference. But even more importantly, and this is the one that caught my attention, that this is the couplings, that this is for the standard model like Higgs. And this is actually couplings of lighter Higgs with ZZ and WW pair normalized with the standard model. So one would mean that it is standard model like. And now you see these different colors correspond to different levels of approximations, and the complete calculation is red. The blue is the misses a few terms, and the point is clear, and it's transparent means that the data do not support this region. And you see that the conclusion, whether the data supports some region or not, depend very much on which correction, whether we have included the corrections corresponding to lambda and kappa or not. So I personally found this as a very sobering exercise. And last but not the least, I wanted to say is that the second nuke and cranny, apart from the night neutralino, is really in the heavy Higgs phenomenology, because heavier Higgs is really a characteristic telltale signature of supersymmetry. It of course appears in two Higgs doublet models and what have you. Again, the prospects for heavy Higgs searches with SM final states, they have inclusive of the latest higher order calculation. There is this report, and I think it's a very nice summary of the current possibilities. Now, what are the new phenomenologically, what are the new angles that one can investigate in the heavy Higgs phenomenology? And that is the heavy Higgs decays into electroweakinos. And indeed, there are these two areas where again you see a lot of current activity. And even more interestingly now, one is looking at whether there are any LLP finds its final states in this. I'd like to advertise sort of two panel session talks by two students from our group who would be talking about 1 and 2. This is again, I go back to Margaret Mühlleitner's paper to just show you the effect on the branching ratios of the radiative corrections. This is basically the corrections that come because of the NLO corrections, and you see there is rather large changes in the branching ratio. So really in the phenomenology of the NMSSM, I think one needs to worry about this. Why are heavy decays into electroweakeners quite interesting? So this is a plot I have taken from a talk by my collaborator Suchita Kulkarni, and what she shows very nicely here is that this is the region of the parameter space in tangent beta and M heavy Higgs, where the branching ratios are large for the TT bar final state, and here a tau tau bar final state, and here this is the case region where the electroweakino final states have good rates. So you see that there is really a complementarity, and that's why one wants to study Higgs into heavy neutralinos, into charginos neutralinos. And we recently analyzed this, and what we did specially was we considered SUSY backgrounds, as well as we studied a viability of using final states with the bees, and by using the tagging the bees, also interesting LLB signals for the heavy charged Higgs. So I'd like to advertise this talk by Amit Adhikari, and I come to the last summary slide, that a light LSP in PMSSM is still possible. That is really the point that I want to make, that only Higgs 125 funnel region seems to be allowed. It's heavily constrained, but it is still possible, and even more importantly, it can be completely tested as far as we can see in the high combination of high energy, high luminosity LHC plus direct detection experiments, and plus the E plus E minus collider measurements of the invisible decay width of the Higgs. In NMSSM2, a light LSP is still allowed. We have studied only the thermal scenario, and really there are not too many constraints. A PMSSM which is extended with the Newark twiddle, a light Newark twiddle is still possible, and there are characteristic signals. So the WIMP paradigm for a light LSP is still sort of alive at PMSSM in NMSSM, and can be tested in the high luminosity or high energy LHC, ILC or CEPC, and direct detection experiments. And the last point that I want to make is that now the state of phenomenology is such that we really need to use the most precise calculations of the Higgs sector, and I think the effect of these new calculations of the NMSSM sector on Higgs phenomenology are still to be studied, and the search for heavy Higgs in the electroweak final states at the LHC understandably are an area of much activity to look for supersymmetry. Thank you very much.
Okay, thank you for your good talk. So I think time is running out. One question, if there is any. One question? If not, okay. Thank you very much, Professor Goldbow. We shift to the next talk. Oh. The next speaker is Professor Saida Ipak. She will talk about particle-antiparticle oscillation and the biogenesis in SUSY. Please.
Trying to make my things play. Sorry, I'm gonna do this again.
Oh, what happened? Okay.
You don't see my screen yet, right?
No.
All right. Share.
Oh, now it's okay.
Yeah. Sorry. For some reason, the menu is okay. Yeah. It's now full screen. Perfect. Yes, thank you for the invitation. I'm going to tell you about biogenesis and specifically some biogenesis scenarios and some interesting SUSY models. And I guess this was called the Ann Nelson Memory Plenary Talk. So I'm going to be showing you some of Ann's pictures as well on the way. So this is a very short history of our universe. only labeled as few specific events that happened in the early universe, like inflation, and then maybe the electroweak phase transition happens. And when the universe is about a few seconds old, light nuclei bind into light nuclei through Big Bang nucleosynthesis. And then our universe continues to expand and get colder and colder. So the era of BBN, the forming of light nuclei, is very important because we know that by the time that this was happening, there was basically no antiparticles left in our universe. Our universe could have started with equal number of particles and antiparticles, but when it came to temperatures of a few MeV, there were no antiparticles left. And this is called the baryon asymmetry or matter-antimatter asymmetry. This phenomenon is quantified with the quantity eta, baryon to photon ratio. This is the number density of baryons minus number density of antibaryons over the number density of photons, or sometimes it's given as a ratio to the entropy of the universe. So this quantity, you can measure it at two distinct times in the history of our universe, actually. One is, as I said, is at the time of BBN. So this plot you are seeing on the right is on the x-axis baryon to photon ratio, this eta. And on the y-axis is different abundances of different elements like deuterium, helium-3, helium-4, and lithium. The abundances of these elements depend on the baryon to photon ratio. The lines are the theoretical calculations, and yellow rectangles are the observations. And the vertical line that is labeled CMB is the measurement from the CMB, actually. So this is the second time we can measure this quantity. So at the time of CMB, it's much later than BBN. And these two measurements actually quite agree with each other, except lithium. But I'm not going to talk about the lithium problem. So these two measurements tells us that eta is about 6 times 10 to the minus 10. Now this basically corresponds to 1 extra quark for every 30 billion quark antiquark pairs. So this is the kind of what the asymmetry is. Basically, it's a very, very, very small asymmetry, but it's extremely important for what happens in our universe later. Now, in order to produce such an asymmetry between baryons and antibaryons, and I will only talk about baryons, but you can imagine this happening with other particle numbers as well, like leptons or some dark matter number. So in order to produce a particle asymmetry between particles and antiparticles, we know that a model of particle physics or some particle physics theory needs to satisfy 3 conditions. These are called Sakharov conditions. The first of these is that the baryon number or some matter number cannot be a conserved quantity. This is because we assume the universe started with equal number of baryons and antibaryons. So if they were a conserved quantity, you will always conserve that equality, basically. So you need to break that symmetry. The second condition is that charge and charge parity symmetries must be violated. CP is a way to differentiate between particles and antiparticles. So you want to break the CP as well. And the third condition is that there must be some out of equilibrium process. And out of equilibrium usually mean out of thermal equilibrium, because in thermal equilibrium, any process that might be producing a baryon asymmetry or producing a baryon asymmetry must be happening at the same rate in the opposite direction, just erasing that baryon asymmetry as well. So you want to break that equilibrium process. Now, when we have those rules, we can just ask if the standard model satisfies these conditions. Standard model actually does violate baryon number, or B plus L number is anomalously violated in weak interactions, because weak interactions only coupled to left-handed leptons. So these are these processes, these weak processes that violate baryon number are called sphalerons, and at very high temperatures, their rate goes like T to the 4 or alpha weak times T to the 4 at very, very low temperatures. Their rate is exponentially suppressed, and the suppression goes like the W mass over alpha weak T. So you can, as you can imagine, at 0 temperature, the suppression will be very, very large, meaning that right now at very low temperatures, our universe is no longer violating baryon number via weak interactions, but at very high temperatures, it might have been violating baryon number. And by high, I mean higher than the electroweak scale. Standard model also has CP violation, again, actually in weak interactions. We know that the CKM matrix has a phase which generates CP violation. And we can ask if the CP violation can be kind of involved in particle in the generation of a baryon antibaryon asymmetry or a quark antiquark asymmetry. And this is of course, a very involved process, actually, how that CP violation feeds into the matter-antimatter asymmetry. But as a back of the envelope calculation, you can say, oh, CP violation in the CKM phase needs to come through the Yukawa couplings, and you need to have all of the quarks involved. And the relevant scales are the quark masses over the temperature. And then if you do that back of the envelope calculation, you find that the asymmetry you will generate just with a CKM matrix is 10 to the minus 20. And this is not telling you about if there's an out of equilibrium process. This is just assuming that there's an out of equilibrium process already. And this brings me to the third condition and asking if there's an out of equilibrium process exists in the standard model. And it does not. There is no out of equilibrium process in the standard model in order to produce the baryon asymmetry. It was thought that maybe the electroweak phase transition would be a first order phase transition, which could be an out of equilibrium process. But in order for that to happen, Higgs needed to be lighter than the W mass. But we now know that it's not lighter than the W mass. It's 125 GeV, so there is no first order phase transition. So baryon asymmetry of the universe is a very strong observation, meaning that we need some new physics beyond the standard model. So this is a very strong case for beyond the standard model physics. And we also know that beyond the standard model physics needs to couple to the standard model, because you want to produce baryons at the end, standard model baryons at the end. It needs to come with some extra CP violation and an out of equilibrium process, because these two we do not have in the standard model, or at least we don't have enough CP violation in the standard model, and we don't have an out of equilibrium process that would generate the baryon asymmetry in the standard model. So this is a very strong case for new physics, and a class of very good models in order to explain the baryon asymmetry are the ones that have some extra scalars in it. These are, let's say, a class of new physics models, and if you add extra scalars to the standard model, which are coupled to the Higgs field, these end up turning the electroweak phase transition into a first order phase transition pretty easily, actually. And I'm assuming that Carlos Wagner will also talk about this on his Friday talk, so I don't want to go into too much detail. But this is also where supersymmetry comes in, because supersymmetry does have a lot of scalar fields that couple to the 125 GeV Higgs field. So it is an amazing scenario, or amazing paradigm, really, to easily I don't want to say easily, but very naturally satisfy the Sakharov condition. So you have extra fields, you can have an MSSM or NMSSM. NMSSM has even an extra field on top of the MSSM, and these all help to make the Higgs transition to a first order phase transition. And if you don't know what a first order phase transition is, excuse me. It is an amazing process. It proceeds via what are called bubble nucleations, and these bubble nucleations are what causes this process being out of equilibrium. And the condition to have a first order phase transition can be told as the Higgs wave at the critical temperature needs to be larger than the critical temperature, basically. So if you get a jump in the Higgs expectation value, you can have a first order phase transition. So this is in order to have this, you still need the new scalars to be not too heavy. And this is also a problem phenomenologically, because, for example, in MSSM, you would actually want the stops to be a bit light, but the stops are not light. So maybe MSSM first order phase transition scenario is not so available anymore, but then you go to NMSSM and then things become easier again. So this is the normal I don't want to say this is a generic supersymmetry electroweak baryogenesis scenario. But today actually I wanted to talk about a much different baryogenesis scenario, which involves another SUSY model. So this the model this interesting model is called U1R symmetric MSSM. And it is basically, this model is you take MSSM with all the ingredients of it, and then on top of the, on the supersymmetric sector, you impose another symmetry, a U1 symmetry, a global U1 symmetry. It's called the U1R symmetry. The R here is not necessarily R parity, just it's a naming convention. So the supersymmetric fields are charged under this U1R. They have +1 charges. Standard model fields are not charged under this R1. So they are neutral. They have 0 charges. The standard model fields. So this is basically what U1R symmetric SUSY is. It has having this global U1 symmetry brings in the very interesting properties. And one of this is that if you look at the gauginos, they now have U1 charges, a global U1 charge, so that they cannot have Majorana masses anymore because they are charged. In order to give mass to gauginos, or in order to give large masses to gauginos, what you end up doing is you add, you turn them into a Dirac field. So you add extra superfields. For each gaugino, you have an extra adjoint superfield. I'm showing here only the Bino case, but we do this for the weakinos and the gluino as well. So for Bino is a standard model singlet. You add a field called singlino with the opposite U1R charge, and the Bino and the singlino will match up basically to make up a Dirac Bino or a Dirac gaugino. And when you have the Bino and the singlino, they can have a Dirac gaugino mass. These are here MD and MD star. They're actually they come from a D term basically, and on top of the Dirac gaugginos, okay, not on. Even though these are Dirac gaugginos and there's a global U1 symmetry, we also know that this global U1 symmetry needs to be broken. Due to the gravitino mass. And when this global U1 symmetry is broken, you can kind of tune how broken it is. When the U1 symmetry gets broken, gauginos actually acquire a small Majorana mass. And this Majorana mass is proportional to the gravitino mass. And if you generate these Majorana masses through, for example, anomaly mediation, the Majorana mass will be proportional to the beta function of here, the hypercharge over the hypercharge. Okay, so this is the Majorana mass is U1R breaking. That's why it will be proportional to the gravitino mass. And this happens with other terms as well. If a term in your potential is breaking this U1R symmetry, it is proportional. It will be proportional to the gravitino mass. So this is the mass of the again I'm only showing you the Binos because that's what will be important for the Majorana symmetry. But the same thing happens for gluinos and weakinos as well. The reason why U1R symmetric SUSY is great is there are many reasons why it's great actually. excuse me, it solves some of the problems of associated with SUSY. For example, the SUSY CP problem. This is, you can have large, large CP evaluating parameters in your Lagrangian, but then they wouldn't end up producing large electric dipole moments for the electron, for example. So this is a problem in MSSM, and this is you don't producing these large EDMs because of the Majorana gauge, because you don't have any Majorana gauge masses, or they are very, very small. And it also solves SUSY flavor problem for the same reason. Basically, you don't have left-right mixing of fermions, or you don't have Majorana gauge masses, so you don't end up producing large flavor changing neutral currents neither. It's also, you have the collider constraints for U1 R-symmetric SUSY is they are less stringent than what is on MSSM, because your gauge genomes are Dirac particles, so some of the production channels are actually not available. So you end up, the collider constraints are much looser for U1 R-symmetric SUSY. So this is great. Sorry. I don't know what this is. Anyway, so but the other reason why it is great is it will end up generating the Bayern symmetry for us. So if we look at the Beano terms, or Beano mass terms again. So we have a Dirac mass term. This is coming from the super soft mass terms, and then we have the Majorana mass term coming from U1 R breaking. So the Beano is actually now called a pseudo Dirac fermion because it has both Dirac and Majorana masses. And also, if we allow for just a little bit of R-character violation, both the Beano and the Singlino will decay to, for example, baryons. So these are baryon number violating terms. So we have a mass term, and through this effective Lagrangian, there's also decay channels, baryon number violating decay channels for both the Beano and the Singlino. And if we look at these two Lagrangians together, they are actually very similar to another system that we are very familiar with. These are meson, these are neutral meson systems like B meson, K bar, K and K-on and the D meson. So if you look at these systems, they have a mass term, and then they have this decay term in their Hamiltonian, and this Hamiltonian tells us that the mass eigenstates do not quite coincide with the interaction eigenstates, so such that for example, for BB bar and KK bar system mixes, and this ends up in what I call meson oscillations, or neutral meson oscillations. So here H and L are the heavy and light mass eigenstates, and B and B bar, of course, particle and antiparticle eigenstates. So this actually, the Beano system is very similar to this, and it also shows oscillation. It also goes under oscillations. And these oscillations are governed by only a few parameters, or really only one parameter, which is this X, basically. X is the mass difference between the heavy and light eigenstates over the decay rate, this gamma. For example, if you start with a system that is fully in the particle, in the eigenstate, or say B eigenstate, as the system evolves in time, it will start oscillating and of course decaying as well. You see the exponential decay envelope, but through these oscillations, some of the mesons or some of the particles will turn into antiparticles, and the oscillation frequency is given by 1 over delta M. And if these oscillations if the oscillation frequency is comparable to the decay rate, you will see very nice oscillations, and the effects of oscillations will be amplified. So it's like a very nice Goldilocks principle going on here. And if the oscillations are too slow, you won't be able to oscillate before decaying, or if they are too fast, they will be washed out. So this parameter X being 1 is a very nice sweet spot for oscillations. The oscillations in the early universe, though, are a lot more complicated than what happens in experiments. And in order to produce the Bayon asymmetry, these oscillations will be happening in the very early universe at temperatures maybe hundreds of GeV, or at least tens of GeV. And why are the oscillations complicated? Because there are, the particles and antiparticles are in a hot and dense plasma. They are not only oscillating, but also they are oscillating in an expanding universe while interacting with other things in the universe, basically. For example, let's say the psi and psi c are now our Beano and anti-Beano states. These little particles are other standard model and supersymmetric particles. We can compare rates of many different processes that are important here. This plot is showing on the x-axis is kind of time in units of the mass of the Beano over the temperature, and y-axis is rates of these processes in units of EV. So of course our universe is expanding. So there's you see
3 minutes.
Oh, how many? 5 or 3?
3 minutes left.
All right, yeah. You see the Hubble rate, and this is the decay rate of the particle. Of course, if the particle decays after the temperature drops below its mass, it decays out of equilibrium. So you have the out of equilibrium condition, and here the oscillation frequency. The oscillations only start when the Hubble rate drops below the oscillation frequency, actually. So the particles need to wait until like the temperature drops below a third of their mass in order to be oscillate. And even after oscillations, even after the Hubble rate drops below their oscillation frequency, they might not be able to start oscillating because there are other interactions going on, and any interaction is basically, if the interaction can tell the difference between a particle and antiparticle state, that's almost like making an observation which prohibits the particle from oscillating into an antiparticle. This is like the quantum Zeno effect, basically. So oscillations can be very, very hard to start in the early universe, and you can find what will happen. How the oscillations will happen in the early universe through solving a set of Boltzmann equations that are shown here. You see there will be this is just the oscillation, this term is the oscillation Hamiltonian. Here you have the scatterings and annihilations of these particles. So these are like all the interactions they can have, basically, and y is the density matrix of your particles and antiparticles. And I'm only talking about Beano here. And on top of these, in addition to these Boltzmann equations, you will also add the baryon and the equations for baryons and antibaryons as well when they are decaying. But when you do that and solve everything, at the end you can actually get an analytical approximation of what the baryon symmetry will be, and that is the baryon symmetry will be proportional to some CP violating parameter in the system, in the decays of these particles, times how the total number of Beanos at the time that when they start oscillating. So you basically need to just know the oscillation when the oscillations start and what the CP violation in your system is to calculate the baryon asymmetry. And here you are seeing the numerical solutions to those to those Boltzmann equations actually. So here, this orange lines are the asymmetry in the BINO-antibino system. The green line is the total number of BINO and antibino. They start with a thermal density, and then they are decaying. And as they are decaying, they're actually oscillating as well. But you can see the oscillations because they are a bit small on top of the exponential decay profile, basically. But these oscillations both produce a BINO-antibino asymmetry, and while decaying, they also end up producing a baryon-antibaryon asymmetry through the R-parity violating decay terms. So, and of course, all of them are going to decay at some point, producing the baryon asymmetry. And here, the BINO mass is set to 300 GeV, and the fermion masses are, the lower line is 10 TeV, and the upper line is 420 TeV. As the fermion mass gets higher, the cross sections for annihilation and scattering cross section get smaller, so you end up with a larger asymmetry. But and the pinkish line here, the horizontal line, is the observed baryon asymmetry. So both of these lines are producing actually more asymmetry than needed. And if you want to be just on that line, the fermion masses in the system needs to be a few TeV, only a few TeV. So this is the parameter space to produce a baryon asymmetry through oscillations of a pseudo-Dirac BINO. And the pseudo-Dirac BINO already exists in U1 R-symmetric MSSM. So that's why I really like this. I really like this model. And I don't have that much time left, but I also wanted to, if I had time, I would have talked about a model from Ann Nelson, actually. So Ann worked on similar oscillation systems. For example, she and her collaborators worked on producing the baryon asymmetry through Mezzino oscillation. So if there's a squark that lives long enough to form a Mezzino, these Mezzinos, just like the neutral mesons, they can also go through oscillations, and these oscillations could end up producing the baryon asymmetry. But another very interesting model from her group was producing baryogenesis via B meson oscillations. These are the B mesons that are in the standard model, basically. And of course, there are some BSM particles and interactions you need to add to this model. But the picture here is that there's some heavy particle that decays out of equilibrium to B quarks. So the B quarks are produced out of equilibrium in the early universe, and then they hadronize into B mesons, and neutral B meson oscillates. And we already know that there's CP relation in these oscillations. And when the B meson decays through, while oscillating, there's CP relation, B meson is out of equilibrium. And then if there's also baryon number violating decays through some BSM interactions, you can end up producing a baryon asymmetry. And this happens, this process, the scenario happens only for if the temperature is below 100 MeV. And I think this is, as far as I know, this is the only model of baryogenesis that works at a temperature that low. And of course, it requires a low reheat temperature and stuff. There are like many details of it, but it does involve only standard model B mesons and only the CP relation in the B meson system. And this is a very nice one-of-a-kind model. Basically, it also generates interesting signals for B factories. It's very beautiful. And with that, I will actually end on this slide, which is a word from Anne. If you haven't read this opinion piece by her that she wrote in 2017, I urge you to. And yeah, I will stop here.
Okay, thank you very much. So one question, please. Is there any question? Okay, Apostolos, please. Your mic. Oh.
Yeah, I'm sorry. I don't have any question, just a comment. I mean, this issue of trying to link gay meson physics and oscillations to the baryogenesis already mentioned by Sakharov. There is a lot of literature well before Nelson embarked on this topic, both in QFT treatments, density formulations, oscillations, mixing and oscillations to different phenomena,
Right.
and a lot of transport equation of lepton asymmetries, not only the oscillation, but also the lepton symmetry will need to be taken into account, because I believe is not discussed in your paper.
Right. Sorry, I didn't mean that. That was like first time that
this resonance
just
enhancement and resonance evaluation was discussed. Resonant leptogenesis was discussed for years.
Right.
That's all the comment I like to say.
Yeah. Sorry, I meant like a model that works, I guess, for B mesons, and even in their model, there's only like a tiny.
I agree. That's a very nice. It's very nice
Yeah.
application to B meson physics. I agree with that. Yeah, that's for sure.
Yeah.
Okay, thank you for your great talk. We need to shift to the next one. The speaker is Professor Kaladi Babu. He will talk about grand unified series.
All right. Can you hear me? All right.
Yes.
Let me go ahead and start sharing.
Yeah. Okay.
Okay. So hopefully you can see the full screen PowerPoint slides, and as well as the laser pointer on it. So my topic is grand unified theories. This would be a broad brush overview of the topic. There are 3 dedicated parallel sessions for GUTS at this meeting. So you will learn much more about the current status and new ideas about GUTS in these sessions. The hallmark prediction of grand unified theories is that protons should decay. I will spend some time in this talk on highlighting this aspect of GUTS. The standard model particles are chiral in nature. Their masses arise through the Higgs mechanism. Chiral theories are also subject to chiral anomalies. So in order to embed the standard model into something bigger, like grand unification, that theory should be anomaly-free. What is shown here are the Dynkin diagrams of the exceptional Lie groups. Each dot in this diagram corresponds to the rank of the group. So you can start from E6, which is the largest exceptional group that has chiral representation. And if you remove one of the dots, you will get E5, which is the rank 5 group, which is SO10. If you remove one more dot, the dot here, you will get E4, which is the SU5. And SU5 has the feature that it is the simplest rank 4 group, which can be used to embed the standard model. The standard model has rank 4. In going from, so I will discuss quite a bit about SU5 grand unification. In going from SU5 to SO10, one gains one feature, which is that it includes the right-handed neutrino, and that leads to neutrino masses. In addition, all the fermions of a given family are unified into a single multiplet in SO10. That's not quite true. It's almost true in SU5, but actually requires 2 multiplets. In going from E5 to E6, what happens is that you have additional fermions. They are vector-like fermions under the standard model. And E6 is also very interesting because there is a possibility that these this extra vector-like fermions could be candidate for dark matter. Especially it contains vector-like lepton doublets and vector-like lepton singlet. So this is actually a very good framework, even without supersymmetry, to obtain gut-motivated dark matter. This would be the quantum numbers would be that corresponding to a vector-like lepton doublet as well as a singlet. I will not actually talk about E6 in this talk, but draw attention to a talk on Wednesday by Borut Bais. He will be, it is dedicated to the E6 Grand Unified Theory. Okay, so motivation for GUTS, there are quite a lot. In fact, any BSM physics is aspirationally would like to be embedded in a GUT. Perhaps this is just to recollect why do we think GUTs are very well motivated extensions. First of all, there is electric charge quantization. Proton charge and electron charge are equal in magnitude to 1 part in 10 to the 21. This is not explained in the standard model, but GUTs do explain that because of the non-abelian nature. There are these various chiral anomaly cancellations, cubic equations miraculously cancel in the standard model. And this is actually automatic. For example, if you start from SO10 GUT or an E6 GUT. A good understanding of the quantum numbers of quarks and leptons. I'll say a little bit more about it in the next slide. Existence of right-handed neutrino and thereby inducing neutrino mass via the seesaw mechanism. This is especially a compelling feature of SO10 based GUT. Unification of gauge couplings with low energy supersymmetry, B-tau unification, as well as a framework for fermion flavor structure, baryon asymmetry of the universe via leptogenesis. All these are strong motivation for thinking about grand unification. And let me explain one, I think perhaps the most compelling reason for GUT is the quantum numbers of all the particles that we know. In the standard model, these multiplexes are scattered with various SU3, SU2, and hypercharged quantum numbers. In a GUT like SO10, there's a very neat understanding of why these quantum numbers are what they are. SO10 has rank 5, and each rank can be indicated by a spin up or spin down operator. And the first 3 spins here are SU3 color spin. The last 2 are the weak spin. And you see that we can understand the hypercharge as a combination of the average of the color spin minus the average of the weak spin. So these random looking hypercharges are actual automatic consequence of SO10 unification. This, I think, is a very compelling feature of for thinking about grand unification. Another feature is an understanding of the masses of fermions, as well as the mixing angles. So here is all the information that we know from the flavor sector of the standard model. It has to do with the top mass all the way down to the neutrino masses. We also know very well the mixing matrix in the quark sector and the leptonic sector. Now, grand unification by itself does not explain all these numerical values, but it provides, perhaps in addition to some flavor symmetry, it provides a good framework to address these puzzles of fermion masses. And I will illustrate it in a few slides later. Okay, this is the well-known unification plot. On the left side is the standard model gauge coupling evolution. They don't quite meet at one point. But they tend to meet. The meeting is not exact. If you have low energy supersymmetry, it is well known that all the 3 gauge couplings meet to at one point. This is perhaps one of the motivations to think of low energy supersymmetry. Now, I should also point out here that the unification scale is of order 10 to the 16 GeV. This is very non-trivial. If the unification occurred, but if it occurred at 10 to the 10 GeV, such a theory would be excluded by proton decay limits. If the unification occurred at a scale above 10 to the 18 GeV, then it won't be very reliable because one has to include quantum gravity. So there is a window between 10 to the 15 and 10 to the 17 GeV where one is consistent with proton lifetime limits and also consistent with the perturbative quantum gravity. And this, it is very, very interesting that the unification of coupling occurs in that window. So this is something that probably is telling us something. Okay, now supersymmetry goes very well with unification. I will focus mostly on supersymmetry, but I want to point out that it is not essential for unification. So if I take non-supersymmetric SO10 unification, it allows for an intermediate symmetry, such as the Pati-Salam symmetry, based on SU4 cross SU2 cross SU2. you can achieve symmetry breaking to the standard model through this intermediate symmetry. And there is a rich literature on this, this analysis dating back to the 1980s. Unification actually works very well. And it is shown here, depending on what exactly the intermediate symmetry is. On the left side, I've given the unification plot when there is a Pati-Salam symmetry, including left-right parity symmetry. Whereas on the right side of the unification couplings without Pati-Salam symmetry at the intermediate scale, but without explicit parity symmetry. Please note that the unification scale is a little bit higher, 2 × 10⁻16 GeV without parity symmetry, but it's on the lower side, a few times 10⁻15 GeV with the explicit parity symmetry. This will have some consequences for proton decay, which I will discuss a little bit later. Okay, so going back to the building up of unified theories, the initial ideas came from Pati and Salam, who suggested that quarks and leptons are indistinguishable. They suggested that the lepton be identified, lepton number be identified as the 4th color. So they extended the SU3 color to SU4 color, and there is a nice arrangement of the 3 colors combined with a neutrino and lepton. And also combining left and right, right-handed and left-handed fields are completely symmetric under SU2 left versus SU2 right. In this model, you see that quarks and leptons are unified, but there is no gauge interaction that would lead to proton decay. So baryon number, although it is not fully conserved in the gauge sector, it is conserved. In fact, there could be proton decay through higher dimensional operators shown here, where proton decays to E plus, E minus, E plus. That comes entirely through the Higgs sector, which does not necessarily conserve baryon number. But there are no baryon number violating processes mediated by gauge bosons in this model. The best limit on this Pati-Salam gauge boson, there is a leptoquark gauge boson in this theory which connects U quark with a neutrino or B quark with a lepton. The best limit comes from flavor physics, K long to mu E, sets the mass of this leptoquark gauge boson to be above 1,000 TeV or so. Now, the Georgi-Glashow SU5 is a complete unification. It has quark and lepton unification. In addition, it has particle and antiparticle unification. You see that U and UC, UC is the conjugate of the right-handed up quark. They are put into the same multiplet, 10 plus 5 bar. And in the initial development, there was no right-handed neutrino, but in order to accommodate neutrino masses, it is good to have a singlet neutrino as well. So what happened, and similarly, so all the fermions of a given family are arranged into 10 and a 5 bar and the right-hand neutrino. Now, once you unify quarks with leptons in the same multiplet and also particles with antiparticles, then baryon number will be broken by the gauge interaction. So the new gauge bosons of SU5 will actually mediate proton decay, and I will discuss. We have to break the SU5 symmetry, and that is achieved by an adjoint Higgs. And in addition, the standard model Higgs will be contained in the fundamental of the SU5, which has something more than what is needed. And this, what is more, is called color triplet Higgs. In a supersymmetric theory, this color triplet Higgs can mediate proton decay that can be quite dangerous. And I will talk about that. These are called the dimension 5 proton decay. As far as the Yukawa couplings, there are only 2 Yukawa coupling matrices, one for up quark and one for down quark. And as a result, one will have a relationship between the down quark mass matrices and the charge lepton mass matrices. The relation MB equal to M tau is considered a success of SUSY unification. When extrapolated down to low scale, it predicts the V quark mass approximately correctly. On the other hand, for the lighter families, MS equal to mu is not a good relation. It is off by a factor of 3 or 4. So that needs to be fixed in any realistic SU5 grand unified theory. Okay, so there is an issue with any grand unified theory which has to do with the doublet triplet splitting. As I mentioned, Higgs, fundamental Higgs contains a standard model doublet, but it also contains this color triplet Higgs partner, and that mediates proton decay. So we have to make it heavy at the gut scale. and bring down the mass of the doublet. And that is the doublet triplet splitting problem. And in minimal supersymmetric SU5, it is done through this superpotential term. And what is needed is that one combination of the two terms, lambda and the bare mass term, should be of the gut scale, but another combination should be at the weak scale. This is somewhat uncomfortable. There are ways around it by going to non-minimal Higgs. I will not discuss it here, but in supersymmetry, because of the non-renormalization theorem, if you do this fine-tuning, it is stable. So we don't have to worry about radiative corrections to this fine-tuned masses. Okay, so these are the X gauge bosons of SU5 that mediate proton decay, the 3 quarks going into a lepton. And the lifetime can be estimated, is roughly given by this expression. What controls the lifetime is the mass of the gauge boson. And the mass of the gauge boson can be calculated from low energy data almost completely. These are the values of the gauge couplings at the Z scale. And assuming that the SUSY particles are known, we will also know what this term is. However, what is, so in principle then, the right-hand side contains the mass of X boson. We can compute it from low energy data. However, there is actually there's one parameter which is undetermined, which is the mass of sigma. Sigma is a heavy color octet. Its mass is not determined. It is a leftover Higgs from the gut symmetry breaking. So we can only predict the mass of the gauge boson up to this uncertainty in this leftover Higgs mass. So there is some, and a small change in the mass of X boson, it depends to the 4th power. So there is some uncertainty in the prediction for proton lifetime. Roughly, it's of order 10 to the 35 years. The current limit on, and the decay mode is proton decay into E plus pi 0. Super-Kamiokande has the best limit on E plus pi 0 mode. It is 1.6. The published limit is 1.6 times 10 to the 34 years. So it is very close to experimental reach. It has not been seen. It is, I think, the proton decay observation is a missing link currently of granular unification. There are efforts to improve this in hyper-Kamiokande as well as Juno experiment, and to some extent in one of the modes, Juno experiment will also be improving this limit. With SUSY, there are these color triplet Higgs-Xeno exchange that leads to dimension 5 proton decay. That turns out to be much shorter and of order 10 to the 31 years typically. This is, of course, this diagram involves the masses of the SUSY particles. So if I put the mass of the SUSY particles at 1 TeV, what you get is 10 to the 31 years. Now, LSC has not seen these SUSY particles at 1 TeV. And please also note that in order to lengthen the lifetime, what would be preferred is to raise the squark masses while keeping the Vino or the gaugino masses relatively low. That will help make it consistent. So the whole idea of keeping all the squark masses around TeV scale is in strong tension with the proton lifetime within SUSY SU5. There have been recent analysis where this squark masses have been allowed to be larger than 1 TeV. And I want to show some results that our group has done. Actually, there was a talk by Champun earlier today in one of the SUSY model sessions. This is from that work. What is shown here is the lifetime of proton to nu bar K plus. The horizontal line is the current limit from Super-Kamiokande. And these are the SUSY parameter space. The green, well, actually, the green lines are consistent with electroweak radiative symmetry breaking, the Higgs mass, etc. And these the red dotted lines also are consistent with the dark matter abundance, correct dark matter abundance. You see that in here, what we have done is we have made sure that all the fermion masses are correct, including the muon mass. And actually, it has a tendency to shorten the lifetime compared to taking the muon mass equal to the strange mass, which is an underestimate. So consistency with the proton lifetime would require the masses of these quarks. This is assuming here we have assumed that the first 2 families have a common mass, M0, 1, 2, and the third family has a different mass, M0, 3, and they have to be about 10 TeV or so in order to be consistent within SUSY SU5. But assuming that they are in the 10 to 20 TeV, there are several points which are consistent with the proton lifetime, as well as the LHC limit and the Higgs mass limit and dark matter constraints. Okay, this is just to get an idea of what kind of spectrum consistency with the proton lifetime would suggest within SUSY SU5. There are 3 benchmark points. You see that the first 2 family masses are order 12 TeV in this benchmark point 1. The third family is even higher, but you do get many of the charginos and neutralinos, and generally speaking, the gauginos are relatively light. And this is consistent. This is what is preferred from proton lifetime is relatively light gauginos and heavy scalars. Okay, moving on, the SUSY SO10 models has the feature that all family members are unified into a 16-dimensional representation. It includes a right-handed neutrino. There are two avenues to break the symmetry. First of all, SO10 can be broken down without changing the rank through either a 45, an adjoint Higgs, or a 210 Higgs. And then one must also reduce the rank. It is done by a 16 Higgs or a 126 Higgs. And finally, there must be electroweak symmetry breaking, which is achieved by the 10 Higgs. So there are 2 possible channels. The one is with the small representation. This has an advantage that the theory is perturbative all the way up to Planck scale. In the second case, one uses a larger representation. The R parity comes out automatic in the larger representation case, but the theory actually cannot be extrapolated all the way to the Planck scale in a supersymmetric framework. So I present here some old work which uses the so-called Dimopoulos-Wilczek mechanism to achieve doublet triplet splitting. It doesn't require fine-tuning as in the case of SU5 that is short. And the reason is that the adjoint Higgs can have vacuum expectation value only along the triplet direction, and it is 0 along the doublet direction. So coupling such as this will leave the doublet automatically light. And I've listed here a set of superpotential that corresponds to the symmetry breaking. This is based on some earlier work with Patti and Tawarkilatse. And then what we found for proton lifetime was that there was a correlation between the dimension 5, that is a nu bar k plus proton decay rate, versus the E plus pi 0 proton decay rate. These two are controlled by the effective mass of the color triplet Higgsino and the X gauge boson mass. If you lower the lifetime, if you increase the lifetime of one, the other one gets shorter. So the net result is both should be within reach of forthcoming experiments such as Super K, Hyper K, and Juno. And this is for a specific SO10 model, but there are many other studies in supersymmetric SO10 as well as SU5 models, which come to the same conclusion, that if you have a complete model, it is very likely that proton lifetime will come out to be on the edge. So this may be an indication that forthcoming proton decay experiments might actually see the proton decay.
Excuse me.
Now I want to turn to how many?
3 minutes left.
Okay, so now I want to, I will be a little bit quick here. I want to show that the simple Yukawa theory based in SO10 with a 10 and 126. Actually, this simple Yukawa Lagrangian can explain all the features of the fermion masses that I listed earlier. And the reason is that, well, there are only 2 Yukawa, these are symmetric matrices, one of which can be taken diagonal. This model has 11 real parameters and 7 phases. There is extensive study of this model. And I want to show that this actually, it's very interesting that this model actually fits all the data, including neutrino oscillation data with large neutrino mixing, small quark mixing. Here is a fit from a recent paper with Saab. The total chi-squared for all these parameters is of order 7. Both for this works very well, both for SUSY as well as non-SUSY. And the prediction for, well, okay, one of the things to see is that we don't yet know the CP violating phase in neutrino oscillation. We looked at it in more carefully to see if we can pin it down, but the chi-square distribution, there are several minima, so it is not really predictive as far as what the CP violating phase should be. There is an absolute minimum, but if I am away a little bit, that still gives a good fit. So that's unfortunately we cannot pin it down. recently, there is this idea that clockwork mechanism can explain small numbers. And this can be embedded. This is for flavor physics, how it works is that the standard model fermions mix with a chain of vector-like fermions, and they have nearest neighbor interaction. And the standard model fermion is a zero mode of this chain. And this can be, so here we have constructed a clockwork SO10, which carries over all the features of this minimal Yukawa sector. Depending on the length of the chain, we can understand the smallness of certain parameters in the fermion sector. And that is shown here. There are two small parameters, epsilon1 and epsilon2. These are determined by choosing the length of the chain appropriately. And then apart from that, all other parameters are order 1, as shown in this fit. So the test of this idea is again proton decay. So here we focus on E plus pi 0 mode, assuming that it's a non-supersymmetric theory. As I already pointed out, this is the lifetime comes out to be close to some 10 to the 35 years. And here is a approximate expression for the proton lifetime for non-supersymmetry. A scan of the parameter space, including symmetry breaking, shows that there are some regions which are consistent with the current limit on proton lifetime, but it cannot exceed much more than about few times 10 to the 35 years. And the branching ratio for proton decaying to pi 0 E plus and neutrino pi plus, these can be more precisely predicted because the overall scale disappears. So the flavor structure determines what the branching ratio is. So these are computed within this theory. And on the experimental side, I have a couple of slides on experimental side. This is actually a slide from Ed Kearns, who gave the talk at BNB circa 2020. This was the situation from the last SNOMAP process from 2013. There were three players, Super K, which is collecting still data. Then there is Hyper K, which was expected to come online sometime soon, and then Dune. These dates have somewhat shifted, but the sensitivity has not changed much. There are two decay modes. Neutrino K plus is the supersymmetric decay mode. These experiments are sensitive to about 1 times 10 to the 34 years for neutrino K plus, and 5 times 10 to the 35 years for the E plus pi 0. So these the predictions that many of the guts are making are within reach of it. And more recently, Juno, which would have a head start, which is quite sensitive to the neutrino K plus mode. Its primary goal is to determine the neutrino mass ordering, but it can be also sensitive to neutrino K plus decay mode, and their sensitivity is 2 times 10 to the 34 years. So it can be quite competitive. There would be also, Juno would have a head start compared to the other experiments. So we are all, what I emphasized the prediction for proton lifetime. It has profound implication for the history of our future of the universe. In the very last stage of the evolution of the universe, proton decay will play an important role. There is astronomers have studied this in detail and consider at a very late time, proton will decay to E plus pi 0. Pi 0 decays to 2 gamma. E plus will annihilate with E minus to give to gamma gamma. So all matter will eventually go into radiation. And white dwarfs will be powered by proton decay. It has been estimated that it will generate 400 watts of power. It is the dominant source of power for white dwarfs. So this is very interesting. This occurs when the lifetime of the universe, a few times the lifetime of the proton. So something of order 10 to the 36 years. This is what. So this is a profound implication for the future of the universe. So let me conclude by saying that SUSY guts are well motivated BSM candidates. Proton decay is their hallmark prediction. SUSY guts are under stress from proton decay limits. Both nu bar K plus and E plus pi 0 decay modes of the proton should be within reach of Hyper K, Dune, and Juno experiments. And for LSC, the preferred scenario is the light gauginos and heavy scalars consistent with the proton lifetime. Thank you very much.
Okay, thank you. Any question? Okay, Ning, please.
Thank you. Hi, Professor. Thanks a lot for your very nice talk. So my question is the following. So you mentioned this clockwork mechanism for the fermion mass hierarchy. So I also remember there were some discussion by George and Frampton, and they said something like, if you extend the SU5 to like SU7 or SU11,
yeah,
can in principle give rise to the 3-generational structure. But later, I didn't see much discussion along this direction. So can you please comment on what kind of
okay, thank you. Thank you for asking. Yeah, I did not discuss it for one reason. I focused on this exceptional chain in this slide here. There is a way of extending chiral gauge theories in the so-called SUN chain, that is by adding more dots here. The main motivation, well, the difference compared to the exceptional chain would be that when one goes to SU6, SU7, etc., you will have more exotics, and potentially by anomaly-free combination of these fermions, you might be able to unify 3 families. That is something interesting. It has not, these kind of models, once you have family unification, the breaking of the family should be such that all the fermion masses and mixing angles should come out correctly. This has not been as developed as the other ideas, but certainly it is an interesting idea of using higher SUN theories in order to accommodate the 3 families into one representation. It is interesting, but has been less developed.
All right, thank you.
Okay, we have no time for more questions. So let's shift to the last talk of this session. The speaker is Professor Howard Bell. He will talk about SUSY predictions from string landscape and the naturalness. So please.
Okay, thank you. Weinberg, who is recently deceased, insisted that the appearance of fine tuning in a scientific theory is like a cry of distress from nature, complaining that something needs to be better explained. i.e., if you've got fine tuning in your model, probably something is wrong. And Einstein insisted that everything should be made as simple as possible, but not simpler. With this sort of guidance, I'm going to examine the string landscape where the MSSM is the low energy effective theory without fine tuning. If you don't believe me, Nima says settling the ultimate fate of naturalness is perhaps the most profound theoretical question of our time. Given the magnitude of the stakes involved, it's vital to get a clear verdict on naturalness from experiment. Now, some theorists will tell you that naturalness is very subjective and meaningless. We probably wouldn't be here because the standard model is extremely unnatural due to the Higgs mass instability. But that really gives us motivation that the theorists have to pay a lot of attention to this issue and try to be clear about what we mean about naturalness and how things can go right or wrong. So we know supersymmetry's got a lot of excellent properties, and that's why we're all here. It even has indirect evidence from virtual effects, namely the gauge coupling unification. The high top mass, the Higgs mass, lies exactly within the predicted SUSY window, and even precision electroweak prefer SUSY over the standard model. But the big question is, where are the sparticles and where are the promised WIMPs? The sparticles, we now know from LHC results, the gluino is bigger than 2.25 TeV, and the top spark is bigger than 1.1 TeV. These can be compared with early bounds from naturalness from Barbieri-Giudice, where the gluino should be less than 400 GeV, and other sparticles have to be quite light. Or you can look at Cassel, Gelencia, and Ross from 2009. The fine-tuning measure goes racing up towards 1,000 when the Higgs mass goes up to 125 GeV. So given this situation, you might say, is supersymmetry a failed enterprise, as is often claimed in the popular press? here's the good old M0, M1 half plane from minimal supergravity model. You can see the LHC mass limit up here in magenta, and the naturalness limits. 3 different naturalness measures claim you have to be in the lower left corner here. So it looks bleak from that point of view, but I think for that reason, we introduced a different naturalness measure based on what is called practical naturalness. Practical naturalness is defined as an observable with contributions O1 through ON is natural if all the independent contributions O sub I to the observable O are comparable to or less than O. And we can apply this to the MSSM because we can minimize the Higgs potential, calculate the VEVs and turn them into the Z mass and relate the Z mass to the SUSY Lagrangian parameters, namely the weak scale up Higgs soft mass here, the superpotential SUSY conserving mu parameter here, and then a whole host of loop corrections going the sigmas. This naturalness measure takes the largest right-hand side contribution divided by mz squared over 2. And if delta is low, that means that you've got a natural model. Namely, a model is natural if all these contributions are comparable to the observed Z mass. The advantage of this measure is that it's model independent, it's scale independent, and the most conservative naturalness measure. But you can also read off directly from here what you need for naturalness. One thing is this mu parameter, which is SUSY conserving, gives mass to the WZ and Higgs boson, but it also gives mass to the Higgsinos. So the Higgsinos have to be close to the WZ and Higgs mass, around 100 to 200 or 300 GeV. This MHU squared is driven negative in order to initiate electroweak symmetry breaking. That means it's got to be driven slightly negative, not deeply negative. If it was deeply negative, then you would have to tune to compensate for that. And it's unlikely the mu parameter would, which arises from your solution to the mu problem, would magically be exactly right to give you such a teensy Z mass. Then the other contributions are all suppressed by loop factors, so they can be much heavier. Here's an example of MHU squared. If it's too low at the gut scale, MHU drives deep negative, and then you have to fine tune. If it's too big, it doesn't drive negative at all, and you don't get electroweak symmetry. So it's got to be right in between here, where it's just large enough that it barely runs negative, and that gives you naturalness. We'll see that there's a mechanism from the string landscape that gives you exactly that green line there. Sometimes it's claimed that nobody knows how much tuning you need. You could do anything, but here visually you can see for different mu parameters what the top 10 contributions are to the fine tuning measure. And your natural, if all these contributions, some are positive and some are negative, are comparable, but as mu gets bigger, then you have to start compensating or tuning, and the tuning turns on really around 350 GeV, corresponding to delta of around 30. Now, that's the electroweak measure. Usually most historical measures have been based on Barbieri-Giudice fine tuning, which takes d log mz squared by d log of a parameter, and the parameters are usually taken to be the different soft parameters of supergravity models. The problem here is it depends on the input parameters of the model. And in fact, you get a very different answer if you put the exact same numerical inputs in, but assume different models. For instance, if I put in exactly the same parameters, but I declare my model as M sugra, I'll get one value. If I put in the same parameters, but declare the model as a non-universal Higgs model, I'll get something 10 times more. So this alerts us to the fact that we don't want parameter dependence on the fine tuning measure. In fact, the parameters are introduced by humans to parameterize our ignorance of the SUSY breaking sector. and what the correlations are between these different parameters. They're not expected to be fundamental in any sort of sense. They would be fundamental in the multiverse, which I'll talk about later on, but not in our particular universe. So for an example, in the well-known model of SUSY with dilaton-dominated braking, you calculate the soft terms as multiples of the gravitino mass, and you can't independently vary M1/2 and A0 because they're all fixed relative to the scalar masses. So while delta BG tells us about the fine tuning in our computer codes, what we really want to know is nature fine tuned or is nature natural? And if you have all correlated soft terms, then the expansion of MZ in terms of mu and the soft terms actually collapses back down into delta electroweak or one soft term. And you can see this also in the anomaly mediation or gauge mediation, where the soft terms are again not independent, but they're all calculable in terms of a single parameter. So the other fine-tuning measure tries to mimic what we do in the standard model to calculate fine-tuning. In the standard model, we got a simple scalar potential, and the Higgs mass is 2 mu squared plus delta mh squared. Well, delta mh squared is quadratically divergent. And if we take lambda to be a large number, then we have to go ahead and dial this mu parameter to be exactly in some teensy narrow range, such that you live, say, if it's in the red with lambda of 10 to the 16, you'd have to pick a teensy range here where you'd live in this blue area. But naturally, the Higgs mass would want to be up here at 10 to the 15 GeV. So people try to use the same thing for supersymmetry, except the quadratic divergences cancel. You can write the Higgs mass as the superpotential mu term plus MHU squared weak, where MHU squared weak is MHU squared at the high scale plus delta MHU squared. And then they write delta MHU squared as this expression, top Yukawa coupling times these soft terms times this large log, which is around a factor of 30 for lambda at the grand unified scale. This requiring this to be comparable to the Higgs mass tells you need 3 third-generation quarks less than 500 GeV. But you have to be careful when theorists break out the SIM signal, then you better watch your wallet because in this case, the actual equation for delta MHU squared is a renormalization group equation, and most of these terms are thrown away for this calculation up here. In fact, in this term, you can see that the XT term contains MHU squared explicitly. And so delta MHU squared and the soft mass are not independent, which is different from the standard model. And in fact, the bigger you take MHU squared at the gut scale, then the bigger is the canceling correction, i.e. these terms are not independent and it fails the practical naturalness criterion. In fact, if you take MHU squared big enough, then you get almost complete cancellation and you get a natural weak scale value of the soft Higgs mass right before you go to no electroweak braking. So that model, should not be taken seriously either. The top quarks can be quite a bit heavier. So if we go to non-universal Higgs mass with a small mu term, now mu can be an input parameter and we take a natural value, then we can plot out delta electroweak. It's this green line here. And you can see that there's plenty of natural parameter space up above the LHC gluino mass bound. So the natural space balloons out here. The Barbieri-Giudice limit is way down here in this little corner. And there's a great difference. Notice that the Higgs mass here is between 123 and 127. So you can accommodate a heavy Higgs and naturalness at the same time. So under this case, the mass bounds from BG and delta electroweak on the mu parameter are the same, but the gluino mass bound goes up to 6 TeV, the top quark to 3 TeV, and the first and second generation quarks and leptons, since they only contribute one loop to the weak scale via teensy Yukawa couplings, these guys can balloon up to 10 to 30 TeV. So in this case, the 125 GeV Higgs and LHC limits are perfectly compatible with naturalness, and there's no crisis in SUSY. And this is the typical spectrum you get. The Higgses and the Higgsinos should all be down here at 100 to 200 to 300 GeV. And the Gauginos can be quite a bit heavier, and the first and second generation matter scalars can live in the tens of TeV regime. So you get a natural particle spectrum, needs only a reshuffling of the usual spectra where Higgsinos lie close to the electroweak scale. Now, sometimes people tell you that we should abandon naturalness. After all, isn't the cosmological constant fine-tuned? And it is fine-tuned, but we do have an explanation that comes from the multiverse and the fact that string theory has a huge number of vacuum states. Each gives rise to different four-dimensional laws of physics. And for instance, each could give a different cosmological constant. Then if the cosmological constant were bigger than about 10 to the minus 119 in Planck units, the universe would expand so much that galaxies wouldn't condense and we wouldn't be here. So this is Weinberg's anthropic explanation for the cosmological constant based on an eternally inflating multiverse. And so far, that's the only really plausible explanation for the teensiness of the cosmological constant. So the question is, can we do the same thing for supersymmetry and the weak to Planck scale hierarchy? And to handle that, Mike Douglas introduced the concept of stringy naturalness, in that a effective theory or observable T1 is more natural in string theory than T2 if the number of phenomenologically acceptable vacua leading to T1 is larger than the number of T2. And this phenomenologically acceptable hides the anthropics here, i.e. you have to get a livable universe. So in a multiverse where you got lots of pocket universes with different weak scales, if the weak scale is too big, then you don't get complex nuclei that can make the atoms that seem to be required for life. So using this sort of a picture, then you can say, well, what should be the distribution of SUSY breaking terms in the multiverse? And in string theory, there's usually multiple hidden sectors containing a variety of F and D breaking fields. And in that case, if no F and D breaking VEV is favored over one or another, then you can compute in the multi-dimensional space of SUSY breaking fields that the SUSY breaking scale should rise as a power law, namely M soft to the 2NF plus ND minus 1. This is easy to see in the case of a single F breaking field, since the F breaking field is complex valued, and the magnitude of the SUSY breaking is proportional to the radius. The red annulus here is much more likely than the green annulus, just because there's more area in the red annulus. So you can generalize this to multi-dimensions and then you get this power law. So even under a single F breaking field, you expect the string landscape to have a linear selection for large soft terms. And if you've got more hidden sector fields, that draw towards large soft terms will be even stronger. So if that's true, then you'd expect SUSY breaking to be up around the Planck scale. But we have to also worry about the anthropics, namely that the weak scale is determined by the SUSY Lagrangian. And so initially people put in a anthropic selection of M weak squared over M soft squared to penalize soft terms from straying too far from the weak scale. But this doesn't work for a variety of cases, namely too big of soft terms can lead to CCB minima, and these have to be vetoed, not just penalized. Furthermore, bigger MHU values we saw actually lead to more natural weak scale contributions than smaller MHU squareds, which drive deep negative. And similarly for the A terms, these big ones, if they get very big, then there's loop corrections in these sigma UUs from the top squarks that actually have a cancellation in them, and they get more natural the bigger the A term gets. So for the multiverse, one can go ahead and invert this relation, use mu as an input parameter and MHU as an input parameter, and then you calculate the Z mass in the different pocket universes that inhabit the multiverse. And then you can understand why natural models should be more prolific on the landscape. Here is a little diagram of MZ pocket universe versus the mu parameter. And if you take parameters for natural models, then there's a wide range of mu values that will land you in the anthropically allowed zone. Whereas if you take unnatural models, then you have to live out here and you only have a teensy range of parameters that will land you in the anthropic zone, but typically the weak scale would be far bigger. And this window, this anthropic window, actually comes to us from John Donahue and his Amherst group back in 1998. They calculated the nuclear physics of too big of a weak scale, and they made this diagram here. This is a log scale with the negative being the bigger weak scales. And the livable window is this white region here. Our domain is this line here. So if you have a weak scale that's bigger than a factor of 2 to 5 from our measured value, then you'll get no stable nuclei and no atoms who violate what's called the atomic principle. And so really the weak scale in the pocket universes has to lie not too far from our measured weak scale. So one can put this thing together and make a similar picture to the cosmological constant. Here's the log base 10 of the weak scale over the Planck scale. If the weak scale gets too big, you get no stable nuclei and an unlivable universe. So we can also see this in the M0 versus A0 plane, where I take MHU equal 1.3 M0. If the scalar masses get too big, MHU doesn't drive negative and you get no electroweak breaking. If the A parameter is too big, that drives the top squarks, squared masses negative, and you get charge and color breaking minima. So those would be anthropically disallowed. But you do get the draw towards large soft terms, the direction of these arrows. And the Higgs mass is 123 and above in this black contour. So that's pulling you towards large Higgs mass. But also the weak scale is close to its measured value in this red region. So you want to get pulled up these horns and into the black and red region anthropically, and that gives you the right Higgs mass. So we can do a sort of scan of this thing by scanning over the parameters of the multiverse. According to a power law, they're not uniform scans, but they're favored for large soft terms. And if you do that sort of business, then you can go ahead and impose the fact that the weak scale cannot be too big. And what you get is a probability distribution for what the Higgs mass should be. With an n equals 0, this would be the usual no favorite power law. You just get a Higgs mass anywhere from 115 to 126. But as you start requiring large soft terms with an n equal 1 power law or 2 power law, then you see these histograms actually pull the Higgs mass up to around 125 to 126 GeV. This is easy to understand from that previous diagram because the A parameter is getting pulled up in value, giving you maximal mixing in the top squark sector, which lifts up the Higgs mass into the region of 125 or so. And if it gets too big, then you start getting too big of contributions to the weak scale, and that's why you get a cutoff here. So it's amazing that the Higgs mass cuts right off near the measured value, so that lends credence to this picture. What about the other soft?
3 minutes.
Yeah. Okay,
3 minutes.
got it. The gluino mass, you see from the landscape, likes to be between 2 and 6 TeV. So the current limits are slightly more than 2, it's not surprising LHC has not discovered the gluino yet. The up left squark can range from 10 to 40, maybe even 50 TeV. So these guys are extremely heavy. The top squark, light top squark, can live from 1 to 2.5 TeV, and the current limits are about 1.1. So again, LHC has barely touched the stringy natural region. So from stringy naturalness, we expect the LHC to see a Higgs boson of mass 125 GeV, but we would expect as yet no sign of sparticles. And in the stringy natural picture, we can go back to the good old M0, M1 half plane. This first one uses the NUHM2, non-universal Higgs mass 2 model, with an n equal 1 draw towards large soft terms. And the density of these dots gives you a more stringy natural region. And you can see no dots lie down here in the lower left, which is the usual region where you'd expect SUSY to be natural. But instead you get pulled up towards this region where you're in danger of getting no electroweak braking. And that's what Arkani Hamed calls living dangerously. If you go to an n equal 4 draw, then it really pulls you up even more towards these upper limits. And so from this point of view, for stringy naturalness, a 3 TeV gluino is more natural than a 300 GeV gluino. So this, I think, is quite exciting. And here's just a final note, since time has run out, a final note on scalar non-degeneracy in the SUSY flavor and CP problem. Since the scalar masses get pulled up into the 10 to 40 TeV range, and the first and second generation get pulled up independent of their Yukawa couplings, then you get a quasi-degeneracy decoupling solution to the SUSY flavor and CP problem. And you expect the cosmological moduli problem to be softened or eliminated as well, since you expect the gravitino mass to be of order of the largest scalar masses. So let me go to my conclusions. Namely, it's time to set aside old notions of naturalness. They've got problems that I outlined earlier. There's plenty of natural parameter space under the model independent delta EW. The main consequence is you get light Higgsinos of several hundred GeV. Other sparticle contributions are loop suppressed, so they can be much heavier. And in fact, this all can come out of the string landscape picture, which prefers large soft terms, and but not too big of a weak scale in the pocket universe. Then you would get a Higgs mass of 125 and sparticles beyond LHC reach. And it does good things for the SUSY flavor and CP problem. And in this case, the dark matter is a Higgsino-like WIMP. But if you have got axions there, axions typically make up the bulk of the dark matter. Thank you.
Oh, thank you, Professor Bell. And before Manuel's question, I would like to ask all of you to turn on your video. Turn on your video. I mean, all the audience, all the participants. We need to take a conference photo. Yeah. Okay, please. And please keep your video on for several minutes. Okay, Manuel, please.
Should I stop sharing to do this? Oh.
I don't care. I had a question on your Douglas string naturalness criterion. Strictly speaking, it's a 0 by 0 division, right? Because there isn't actually any explicitly constructed string vacuum that is phenomenologically acceptable, as far as I know. In the sense that it reproduces what we know about nature, quark masses, fermion masses, blah, blah, blah. So
yeah, well, the whole idea here is,
if you take phenomenologically acceptable seriously, then it's a measure of set 0, it seems to me. Sorry,
yeah.
Set of measures, well, rather.
I think the idea here is if you really have of order 10 to the 500 vacua, the likelihood that you're going to have your grad student derive exactly the right one out of that 10 to the 500 is pretty teensy probability. So for that reason, Douglas advocated a statistical, going to like statistical mechanics, trying to do statistics on the vast ensemble of stringy vacua, and to drive.
What exactly do you mean by phenomenologically acceptable then?
Well, in this case, we assume that the MSSM is the 4D effective field theory below the gut scale, and then the weak scale is a derived quantity. It doesn't, the Z mass is not 91.2, but it can be anything because you're no longer tuning, but you're getting different parameter values in different pocket universes.
Hi, Professor.
Oh, yeah.
Professor Beck, you should create the screen sharing. Then we
Okay,
can take the photo.
I will stop share.
Oh, thank you.
Does that work? So yeah, hopefully that answers your question.
But, well, not quite. I mean, the assumption is then that you still have lots of vacua, high statistics of MSSM vacua with right quark masses, blah, 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 everything correct. And only your soft breaking terms are, you do statistics in that. That's actually quite a strong assumption, it seems to me.
Well, it is, but this is what Weinberg assumed also with his cosmological constant prediction, that the standard model was the low energy EFT with everything okay, but only the cosmological constant was varying. Now, Arkani Hamed et al. Have written a paper where they say that the terms with mass values are the ones that should scan in the landscape, but the gauge couplings and Yukawa couplings not necessarily so. And so that sort of picture can emerge where you can look at the ensemble of MSSM vacua with the varying soft terms and try to gain insights as to, what the weak scale value implies for the SUSY, what the soft term should be, and consequently, that's why you can make predictions on the particle masses and Higgs mass.
Okay, thanks.
Okay, because time is very tight, this session has to stop here. And the following parallel sessions will start very soon, in 2 minutes, I guess. Okay, thank you for all the speakers for the nice talks, and the audience, all the participants for your attendance. Have a good day.
Thank you.
Okay, thank you for doing the session, being a good chair.
Thank you.